name's Joe Testa. I'm the co-founder of Positron Security. It's a local computer security company. And I'm here to present on a new open source project called Bitclamp. It's a tool to publish documents, files into the Bitcoin blockchain. So I'm going to go into the details of that. I know not everybody is experienced with Bitcoin, so I figured I'd give a little bit of a primer. To really go into all the details of Bitcoin would be its own presentation easily. So I'm just going to give a quick primer here. Actually, a show of hands, how many people have experience, at least some experience, using Bitcoin? Okay, about half. So here's a quick primer. Bitcoin's a 100% digital currency. Uses strong cryptography to protect against fraud. It's designed to be decentralized, and I guess you can kind of say it still is, although that's a little debatable these days. Payments can be anonymous. Common thing people like to say is that Bitcoin is anonymous. I would say that they can be anonymous, depending on how you go about using it. And payments are permanent. That's one of the central things behind it, is that if you send a payment to somebody, it's there, it's gone forever. Unless they choose to send it back, that's there forever. So the big question is, why would you use Bitcoin to publish? Like I said before, anything you do in the Bitcoin network, it's permanent. So that's a pretty interesting property to have if you're trying to publish files or something like that. It's also, like I said before, semi-anonymous. To remove anything, I said before it's permanent. Technically speaking, you could, in theory, remove something from the transaction log, but it would require just ridiculous amounts of computing power. You'd need about 1,300 petahash per second, or something around there. That's just a massive amount of computing power. So it's very unlikely that anybody else has that amount of power. So this is the perfect situation for whistleblower type documents. The ability, if you could figure out a way to put data into the Bitcoin blockchain, which is the transaction log, you know, those documents are going to be there, available to everybody, and they're going to be there forever. So here's an outline of what I'm going to cover. I'm going to go into a little bit of some technicals behind Bitcoin and some of the background. There's two prior methods of publication. This idea of publishing into Bitcoin is not new. I'm not presenting that as new. That's been done before, but the existing methods have some pretty serious shortcomings, so I'm going to talk about that. And then I'm going to unveil a new method that I came up with myself and analyze what its properties are. And then hopefully I'll have time to talk about some of the more advanced features. So a little bit more background, just to understand the later parts of my presentation. So Bitcoin has its own scripting language, which is pretty interesting. So if I send coins to some address, there can be a script embedded in it so that the recipient has to satisfy the logic somehow. So this language, it's stack-based. There's conditional statements. There's bitwise logic you can do. There's arithmetic that you can do in this language. And of course, there's cryptographic functions. Many of them for standard transactions are actually disabled, and I'll get into that a little bit later. And if anybody's interested, there's a link to the documentation of this scripting language. So a little bit more background. Transaction fees. Trying to think how to describe this because I don't want to get too deep into Bitcoin. But the people that process the transactions in Bitcoin, they're called miners. What they do is they just run the SHA-256 hash function over and over and over again to try to what's called solve a block of unconfirmed transactions. And the idea is that if you succeed in this, you get paid. You get a block reward. At this point, the block reward is 25 Bitcoin. So that's their motivation for doing all this hashing to confirm transactions, is that if they succeed at it, they get a whole bunch of money. And the current price is, I think, $450 per Bitcoin. So that times 25 equals quite a lot of money. So that's the block reward happens to be the main motivator, but it's not the only one. There's transaction fees that can be attached. Now they aren't exactly mandatory, but the transaction system is pretty much a free market. So if I want to send money to some other person, if I want to get that transaction confirmed quickly, I would have to attach a fee. I could try to cheap out and either do no fee or a low fee, but the miners are self-interested. So if they see, well, here's like a whole bunch of high fee transactions, I'm gonna prioritize these, and I'm gonna deprioritize the low fee or no fee transactions. So it's a free market, so I can try to cheap out if I want, but it just means my transactions won't be confirmed very quickly. So the current rate is 0.0003 Bitcoin per kilobyte, which is a pretty weird. It's a pretty weird system. It's not like in a traditional system like credit cards or PayPal or something where they take a percentage of what you're transferring. This is a fee per kilobyte, so that's per however large your transaction is in bytes. So it's a pretty weird thing that trips up a lot of users because it doesn't really make sense. If they send, sometimes, you know, if you send $1,000 worth of Bitcoin to somebody, you might pay a very small fee, but later on you might send, you know, a small amount of money and suddenly you got to pay, you know, 5 times in the fee. It doesn't entirely make sense. It just all has to do with how the transactions are structured under the hood. So now I'm going to go into the first method that somebody used to put data into the blockchain. A little bit of background on this first. So to generate a Bitcoin address, this would be basically how it's structured. You start with an ECDSA key, the public key, and you run two hash functions on it. First SHA-256 and then RIPEMD 160. You prepend a 0 byte and then you append some checksum, which doesn't really matter in this context. And then you base 58 encode it all to get that string in the middle. Now that base 58, it's basically base 64 just with some of the characters removed. And that's basically it. The punchline is that base 58 is reversible just like base 64. So one thing to notice is that the RIPEMD 160 output, that happens to be 20 bytes. So if you wanted to publish 20 bytes of data, you just set your data to be that 20 bytes, excuse me, and then you prepend that 0 byte and append a checksum, and then you generate that address. Let me back up there. So basically, instead of calculating that RIPEMD output, you just set your 20 bytes to be that, calculate the checksum, prepend the 0 byte, base 58 that, and there you go. You've got a Bitcoin address that appears to be valid. Now the network doesn't know that it's invalid. It just sees that address and says, okay, well the checksum's valid, so okay. So pretty much you can do this over and over again. You just generate all these fake addresses and just send a very tiny amount of Bitcoin to them. And in a single transaction, you actually have up to 256 outputs. So what that means is in a single transaction, I can say, all right, I want to give, you know, half a Bitcoin to this person, 0.3 Bitcoin to this person, 0.003 Bitcoin to this person, and so on. So one transaction could actually have 256 of those, in theory. So in one transaction, you've got 20 bytes times 256, so you've got about 5K. Actually, it's exactly 5K. Which is kind of small to publish a lot of files, so if you've got something bigger, you just use another transaction. So just as an example, just to go over this again, so if you have the text A, B, C, D, E, F, G, you just first convert it to ASCII, and there's the hex, 65, 66, 67. You calculate that checksum, you run it through that base 58, and just send money to that address and just keep repeating. So somebody used this method to publish the original Bitcoin paper, the original PDF. I think it was maybe 175K. So yeah, they use this to publish into the blockchain already. When I was making these slides though, I couldn't find it anywhere, which is kind of funny because I think that says a lot about this publication method as a whole. It's like, okay, it's there, but I can't find it, I can't extract it, so how useful is it really? I mean, it might as well not be there. So major disadvantages to this method. You're actually destroying coins because you're generating bogus addresses. Those addresses don't have a valid private key. So nobody can ever spend those coins again. They're just destroyed forever. A big one that, and this is what the Bitcoin developers really had an issue with, is it pollutes the UTXO database. That stands for the Unspent Transaction Outputs database. So that's pretty much what it sounds like. The Bitcoin network will maintain a list of, okay, at any given time, here's a whole list of all unspent transactions. That way, when a new transaction comes in, the network can say, oh, okay, you're referencing this one, which happens to be unspent. So therefore, it passes this check. So the problem is, with that method of generating all these bogus addresses, those transactions will always remain in the UTXO database. They will never leave. Because if a transaction then becomes spent at some point in the future, it gets removed from that database. So all those entries are in the UTXO database and they will never leave, so it results in pollution over time. So the Bitcoin developers had a big problem with this. And I'll get into that probably in the next slide. So other major disadvantage is that it's very expensive. The current minimum that you can send to an address, I think, is this 0.000000504 Bitcoin. So you would have to send that minimum amount for every 20 bytes you want to publish. And that gets really expensive. And on top of that, you have to pay transaction fees. So one megabyte, if you wanted to push out with this method, would cost about 0.6 Bitcoin, which at today's rate is $255. So that's pretty expensive for just 1 megabyte. So yeah, like I said before, the developers really didn't like this UTXO pollution. So they came up with a compromise. Like I said before, the Bitcoin network has a scripting language. So one of the opcodes is this op return, which in programming languages is basically saying like return false. So they changed this to allow anybody to put at first 40 bytes and then I think they extended it to 80 bytes of just arbitrary data. And the punchline here is that OP return always results in failure, so the transaction can never be spent, and the network knows this. So it knows that it doesn't ever have to add it to the UTXO database to begin with. So it prevents this pollution problem, but you know, on the other hand, you've only got about 80 bytes to work with, which is very tiny. That's one of the main problems with this. Is that the payload is so tiny with just 80 bytes. If you wanted to reference another transaction to say continue publishing blocks, with just 80 bytes, the transaction IDs I think are 32 bytes. So you'd have to reference that in the header, and then you've only got 48 bytes remaining to do a payload, and It's just extremely inefficient. If you want to publish anything large, it's extremely inefficient. One of the things I said before is that you've got up to 256 outputs. So one might think, okay, well that's 80 bytes times 256. I guess that's maybe not so bad. No, unfortunately, there's a restriction that says you can only do one OP return per transaction. So you're just limited 80 bytes per transaction, period. Regardless, people are using this method still. They're using this to publish hashes. And there's a website here, eternitywall.it, that lets you just type in a box and click publish, and you just publish some small amount of text in the blockchain. So this is a method that's actively used, just in a limited fashion. So here's my goals for a new method. Since these two existing methods have so many downsides, there's no way that you can use them to publish files of arbitrary size. So that's one of the goals that I have, is I want to be able to publish a file of any size. I also want to be able to search and or extract the data. Like I said before, if you can't do that, the data might as well not be there. I also want to minimize the cost, and I want these tools to be available to everybody. So I started digging around the Bitcoin code, and I happened upon this isStandardTX method call. And this happens to be the gatekeeper to whether or not a transaction will be relayed across the network. So if you wanted to play around with any of the various scripting language components to try to jam in data into a transaction, you need to pass this isStandardTX method call. So I started by analyzing that. I started looking at these multisig addresses. That happened to be the key to solving everything. So a little bit about these multisig addresses. It's kind of an obscure feature, but pretty interesting. So it's a system, so you can say, here's M keys, public keys, and to spend these coins, any N of them are needed, and that's up to 15. So what you can do is you can say, all right, well, here's 7 keys, and in order to spend these coins, any 3 signatures need to be present. Or you can say, here's 11 keys, any 5 of these need to be present. So this can be kind of useful if you want to protect, let's say, against malware or theft. You can say, all right, here's a 2 of 2 scheme. So let's say you have 1 key on your laptop and 1 key on your phone. Let's say your phone, you lose it or somebody steals it. So they recover the key from there. Well, in that case, whoever stole your phone can't spend your coins because they would need a signature from the key that's on your laptop. So it's a separation of keys in order to allow spending to occur. And just FYI, there at the bottom, I just have an example. If you wanted to spot out what a multisig address looks like, they begin with the number 3 versus, I think the standard ones begin with a 1. Just gives you an easy way to identify them. So I looked at this and I said, all right, well, there's 15 keys, up to 15 keys that are supported, so let's use them. How about we do something where we generate 1 legitimate key, and we set up a system that says, all right, only 1 out of these 15 are needed. And the other 14, since 1 is the legitimate key, the other 14 happen to be just data. That's the data that you want to publish. So in this case, the keys that are presented are the raw ECDSA keys, and those are 32 bytes. So you've got 14 times 32 equals 448 bytes. And this isn't just per transaction, this is per output. So you can have 200, in theory, I'm going to get into the restrictions later, but in theory, 448 times for every 256 maximum outputs. That's quite a lot. So the advantages, large payload. Another big one, transactions remain spendable. So because the coins are never destroyed, because you always have that one legitimate key to ensure that it remains spendable. That means the transactions are spendable so that the UTXO database doesn't get polluted. So that's a key point right here. You only need to pay transaction fees for this, if at all, and I'm going to get into some situations later. Now I said before it's 448 bytes per output, but unfortunately there's a hard limit of 10,000 bytes, so your transactions need to fit within that. But I think you can get somewhere around 90 to 95% efficiency. Because there's going to be overhead in terms of, like, data structure and your transaction and so on. So you can get pretty close to that 10,000 bytes, and maybe, I don't know, 9,000 bytes would be your data payload. So that's pretty good. So here's some numbers. To publish 1 megabyte using this method will cost up to 0.35 Bitcoin, which is about $150. Now, notice I've got in italics there up to, and I'll get into later some more about that. And contrast this with the about $255 guaranteed you will burn in the first method. So that's pretty good just right off the bat. So the fastest publication time that you could get with for 1 megabyte would be 20 hours. And that's because Bitcoin targets about one new block about every 10 minutes. So if you're publishing about 9,000 bytes every 10 minutes, it's going to take you roughly about 20 hours to publish a megabyte. Now there's a trade-off, as I kept alluding to, there's a trade-off between the fees paid and the time to publish. So if you wanted to pay less and you were okay with waiting longer, you just reduce your fees. And I don't have any hard data as to the effects of this, but you could lower your transaction fees lower and lower until you got like a publication of time of days or weeks or even months. And depending on what situation you're in, you might not care. Like, okay, it takes me 6 weeks to publish this this document. I'm okay with that. Remember, this isn't like your own personal cloud backup service. Like, oh, I just took pictures of me at the park. I want to store them in the Bitcoin blockchain. That's not really the use case here. This is something you want to publish something very serious and you want it there forever, that nobody can ever delete. So in that kind of situation, you might be okay with, all right, it's going to take 5 weeks to publish something, and I'm going to pay, I don't know, $20, $30. Might not be so bad. One thing to notice is that Bitcoin isn't the only thing that you can publish into. There are other cryptocurrencies that pretty much started by copying the Bitcoin source code and then just making a little bit of changes from there. Litecoin was one of the first ones, and then a lot of other cryptocurrencies started off of that. So those cryptocurrencies all inherited, unless the developers actively went back and disabled them, they all inherited the multisig functionality. So you can publish into other blockchains like Dogecoin. So here's a little bit of analysis of that. In Dogecoin, the block time is 1 minute versus 10 minutes for Bitcoin. And another major advantage is there's extremely low, or even a lot of times no transaction fees at all. The disadvantage is, though, the network has a much lower hash rate than Bitcoin. And the hash rate, the collection of all the hash rate for all miners, that's what specifically protects the blockchain from being reverted. So it is a bit more vulnerable to transactions being reverted, which means, you know, publications being reverted. There's also a question of, will it survive? Dogecoin was very popular about 2 years ago, and then in recent times it died down and then sort of leveled off. So there's still more of a question of, will it survive? And if we're talking about this context where I want to publish something permanently, there's sort of a question mark there. But maybe that's okay. I mean, it's a trade-off. There's many trade-offs in this whole system, so it might be okay. You might be okay with that, because those advantages are pretty massive. One megabyte can be published for just 24 cents because the transaction fees are just so low. And because that block time is 10 times faster, you can publish a megabyte in 2 hours. Even more is the fact that their blocks tend to be mostly empty. So there's no contention there. What that means is you can probably flood the network with multiple transactions per block. So it's possible that you can get much less than 2 hours. You could potentially publish a megabyte in just a matter of minutes. Let me just check my time here. So here's some special features that I have implemented. It by default supports temporal encryption. So if you go publish a file, by default it'll use GPG2 to encrypt the file with a random key. And in the last block, the key is divulged there. So this protects the content while you're publishing, which might be a very useful feature to have. You might not want anybody seeing what it is, you know, that's being published until it's done. On the other hand, you might be in a situation where you want to jam in as much as possible, as quickly as possible, because maybe somebody's onto you and they're about to stop you. So you can turn off encryption. So that's up to you. I began implementing another feature, a Deadman Switch, and this is pretty interesting. This can be an insurance policy for some people in some very special situations. Let's say, okay, so the idea is that you would publish an encrypted archive, except that last block doesn't have the key. And then you can set up some kind of external process so that, you know, this person would have to check into on some kind of regular basis, like every X hours or X days or once a week or something like that. And the idea is that if this person disappears, if they get arrested or fall down a flight of stairs, this process will automatically publish the key. So it can be an insurance mechanism. This is called a Deadman Switch. I don't have it fully implemented yet in the code, but it's coming. So a pretty big question I think that comes up would be, can Bitcoin block this? Can the developers block this? And I think there's some things that they can do, but not really without changing the functionality of those multisig, the support for the multisig functionality. So they can reduce the number of keys from 15 to something lower, but you know, that obviously can interfere with what people are legitimately using it for. And if they did that, you can just bump up the number of outputs per transaction. So you should be able to always fill up that 10,000 byte limit one way or another. So it seems like they probably can't block this. The thing is, they might not even care. One of the biggest things they cared about in the beginning was the UTXO pollution, which would create a pretty major problem for them. And this system doesn't result in that, so I'm thinking they probably don't even care. On top of that, the miners still get transaction fees, so it's not like you're abusing the network in any way. The miners are still getting rewarded for this data that you're giving them, so I'm thinking they might not even care. So the code I've got available right now, there's the link to it. It's up on GitHub. It's currently in beta. I kind of wish I had more time to finish some of the features and things like that, but unfortunately, I could only get it in the state of beta. So if you guys want to test it out and help me get that to version 1.0 stable, I'm hoping that'll be done by the summer. And here's kind of the punchline of this whole project, is the fact that I don't want this to be some kind of just another nerd tool. You know, it's a command line Python application there on GitHub. I mean, how many end users are going to be able to figure this out? You know, the techies can, but you know, normal everyday people, it's like, what's a Python script? You know, how do I command line? Like, it doesn't make any sense to them. So I don't want this to be some kind of like obscure hacker tool. I want the general public to be able to do this. So I'm going to be writing a website front end for it. So people will be able to go to a website and you'll be able to browse. Here's like the last 10 things in the Bitcoin blockchain. You know, here's the last 10 things in Dogecoin. You'll be able to click, download stuff. There'll be a search bar in there so you can search, you know, based on file name, based on file type, stuff like that. And the ETA, I think, of that is also going to be the summertime. And of course, you'd be able to publish on the website as well. So that's really the punchline for me for this project. Any questions? Yes.
So all your data is going into the extra addresses for the multi-transaction, right? So,
yeah.
So I'm just wondering what happens regarding increasing the potential for collision between addresses.
Yeah, I suppose that can happen, but those addresses, whatever, so it'll send like a very, very small amount of like the bare minimum of Bitcoin to that address, but what gets sent there is not controllable except for that one legitimate key. So, like the bogus keys in this case cannot be used to control those funds. The only thing that could be used to control the funds would be that one legitimate key. The way it works is you start off the process. You say at the command line, you say, here's a file I want to publish, some other options, and it'll say, all right, to start it off, send X amount of Bitcoin to this address. And then you externally send that to that address and it'll notice that. And then it starts sending the Bitcoin back and forth to itself over and over again, every transaction level. And each time it's publishing about, you know, up to about 9,000 bytes or so. So every time it's sending these coins back and forth, it's using that one legitimate key that only you have because you generated it special for your own publication. Does that answer your question?
Not entirely, but I mean, I think this is probably a longer conversation.
I think were you trying to ask, like, is it possible to for somebody to hijack the?
No, I mean all of that, right? But some of the other thoughts that came to mind was just as far as the address space. I mean, the address space is immense, but all those addresses are being generated in a very random way right now. As you start to generate addresses based on things that are not random, I just see that at some point there could be collision between users using this, or I don't know. It just seems that they're monkeying with the math, right? And it's cool, but I just wonder if there's an inherent flaw there because we're kind of taking things that are more deterministic and we're replacing something that's very random with that.
Yeah, I didn't include any slides on how these multi-sig addresses I'm generating because I kind of thought I was going to throw way too much information at you guys anyway. as it is. But this multi-sig address at the bottom, the way that's generated is a hash of all the 15 keys, the 14 fields which are data, and then the one legitimate key. They all get hashed in a certain way, eventually leading to that. So those 14 pieces of data may not be entirely random, you know, because if everybody's publishing the same file over and over again, it's going to be, those are always going to be the same. But everybody generates a random key themselves. Okay. So then you append all this stuff, and there's a little bit of randomness in there because of that unique key, and then all of that is hashed to get that multi-sig address. Okay. And so then funds are sent to this, and then another address is generated, funds are sent to that one, and so on. It just,
so you actually have two legitimate addresses to be able to send back and forth?
Yeah, well, it's always maintaining, yeah, it pretty much always maintains two, and just keeps sending funds back and forth, and then in the transaction it says, oh, and by the way, here's all the 15 keys. That's included in there as well. Yep.
Yes, you mentioned this was, you're going to include an easier method of trying to find this data in the blockchain once it's out there. How do you plan on doing that?
That's another slide that I intentionally didn't include, just because I didn't want to flood people with information. So because you can publish, you know, about 9,000 bytes per block, there's pretty much, it starts with a publication header that says here's the file name, here's a description of what's being published, here's the file type, and here's whether it's encrypted or not, and then the continuation block will say here's a reference back to the prior transaction that has the prior data, and then basically they're all chained together, and that at the end there's like a termination header. So basically to search through the blockchain, you just parse through and just keep looking for this header, and then once you find that,
you have to have the full blockchain.
What's that?
You have to index the entire blockchain then, when you're running to be able to search through all of the transactions without having just the UTXO set, you're not going to have access to all that data without having TX index 1 or whatever set up.
Yeah, you do have to enable the TX index. Yeah, so yeah, once you enable that, then you've got all the data you need, and you use the RPC. It uses the RPC calls to just pull down all the raw data, and it just pretty much looks for that header. Right now, the code doesn't support searching. That's obviously a very major feature. Right now, the code just supports like real time. It just pulls down what's being published in real time, and that's just a current limitation. Question over here.
Yeah, do you see greater throughput being possible with segregated witness?
Greater throughput with
segregated witness?
Segregated
witness. It's an improvement in Bitcoin.
Oh, is it one of the proposed
Yeah,
things?
it's like almost it like just got pulled into the main Git repository.
Oh, okay. Yeah, no, I actually don't know anything about that, so I don't know.
Basically, it makes like all the transactions cheaper.
Okay. It's called segregated witness?
Yeah, basically it separates the signature of the transaction from the transaction itself. And so like miners, they still need to give the signatures, but you can choose to run a full node without them as those signatures. So it effectively increases the block size to about like 1.5x.
Oh, okay. Yeah, I suppose I should look into that. Any other questions? Oh, yep.
Have you considered or looked at Ethereum for this kind of project?
I've heard about it. I've read a bit about it, but not so much.
Worth your time.
Is it? Okay.
Yeah.
All right. Yeah, I suppose I will. Any other questions? All right. Thank you very much. I'll be around if anybody has any questions.